Archimedes joins Dorothy on her journey to Oz so that he can be granted a new toga from the wizard. On their way, they encounter a stranger and decide to ask for help.
Excuse me, sir. What do you want?
Well, I'm Dorothy. I'm Archimedes.
My name is Sir Isaac Newton, known for my good looks in discovering gravity. Well, we need to get to the bottom of that hill before the witch disappears because I need to save Mittens. Can you help us? Sure, I can help you. According to my calculations here.
We need to use Newton's second law. My law states that the acceleration of an object is directly proportional to the net force acting on the object and inversely proportional to the mass of the object. In other words, F equals ma. The first thing we need to do is consider everything we know. The initial velocity of Dorothy and her sled should be 1.4 meters per second. The length of the hill is about 45 meters. And the time we need to take to get to the bottom of the hill is 30 seconds. Then the witch will disappear. Also, the coefficient of friction between the sled and the grass is 0.84. The mass of Dorothy and the sled total should be about 60 kilograms. And finally, the angle of inclination of the hill is 30 degrees. Now we're all set to start solving for the force needed to push Dorothy and the sled down the hill. It's very helpful to draw a free body diagram of our situation, labeling all the forces acting on our object. Notice I'm putting the force of gravity down with the angle of inclination measured to the y-axis. I'm also labeling positive x in this direction, because that's the direction of motion. Now, first we need to solve for the acceleration of Dorothy and the sled going down the hill. We can use this by using the equation delta x equals VIT plus 1/2 AT squared. After some careful calculations, we can solve the acceleration to be 3.1 meters per second squared. Now we need to use this acceleration when solving for the force in the x direction. We can say that the sum of the forces acting in the x direction is equal to the mass times the acceleration in the x direction. Using our free body diagram over here, we can add up all the forces acting in the positive x direction. So F minus the force of friction plus the component of the force of gravity acting in the positive x direction, which would be Fg sine of 30. That will equal mass times acceleration. The force of friction is equal to mu times the normal force. Fg is equal to mg. Now we need to do a side calculation to solve for the normal force. Fn, in this case, will equal the component of gravity acting in the y direction, as you can see in our free body diagram here. So that will be mg cosine of 30. We can use this substitution in our big equation here. Okay, this is a very long equation, but when you plug it in carefully, you get your final force to equal 13.9 newtons. This is the force needed to push our entire object down the hill and get you down in 30 seconds before the witch disappears. So that is our answer, and that is how we do it the Newton way.
Go.
So we should be able to get down in time. Alright, where's the sled? There's a sled. Hey, look! Alright. Wait, before you go, Oh, look, we made it! We made it! Let's go! Let's go! Come on!
We made it.
Nice work for amateurs.
There she is! You'll never get me, my monkey protecting me.
Maybe we should shoot the monkey.
I think we should just tear him down.
No!
Now what should I do?
Mess up her magnetic domain.
How?
Hit her with it.
No! Tell me, baby, don't hit it. Take that. And that. I think she's dead.
Now we can go see the wizard.
Yeah.
I am the physicist of Oz. What would you like?
Well, I'm Dorothy, and I want to go home.
I'm Archimedes, and I want a new toga.
I'm Sir Isaac Newton, and I want to know whether light is a particle or a wave.
You can get home by clicking your heels 3 times.
Okay. What about them?
Come with me and I'll give you a new toga.
Yes.
What about me?
Just call it a waveable.
Brilliant!
There's no place like room 523. There's no place like room 523. There's no place like room 523. Oh my gosh. I just had the craziest dream.
Thank you.